All right, so this is to clarify from yesterday. Here's the idea. If I have a bag that contains, I already know that in my bag is 0.7 molar solution, okay? And I put that bag of 0.7 into my flask of 0 molar solution, basically pure water. What should happen to that bag?
Swell up.
She says swell up. Agree? Don't get all swollen. It will swell up. Because, remember, the rule, water will always travel towards the hypertonic solution. And this 0.7 is definitely hypertonic to 0. Okay? So if we were to picture our flask that's 0 molar, here's all our little water molecules. In our bag is 0.7. So here's a bunch of solute that can't pass. And here are our water molecules. Obviously, if only water can pass, there's a much higher chance of a water hitting from the left and going towards the right. Even though water can go the other way, just by random chance, this bag is going to get bigger. What about in the 0.5?
So 0.5 would be kind of naturally so close to 0.7, but you're going to have some water coming in.
Good. It will swell, but not as much. And let's imagine why that's going to happen, because again, here's our 0.5. It's got some sugar molecules in it. And our 0.7, though, has more sugar molecules in it. I didn't draw it as nicely. So here's our 0.7, there's our 0.5. We still have a higher chance of water going to the right. But it's not as high of a chance as this first one, so we're probably going to see a little more water go to the left. So this will gain weight, but it shouldn't gain as much weight. How about in the 1.0?
Water will leave the bag.
Good. In the 1.0, we have the opposite situation. Now, here on this side we have all this sugar. And on this side there's more water. And so now the chances are higher for the water to leave the bag. Alright. Now here's my point. We could graph this. So let's imagine making one of our T graphs that I taught you how to make, that you're going to have to know how to make on the test. And we got 0, and we've got 0.5, and we've got 1.0. And we said that in 0, this bag will gain probably a lot of weight. In 0.5, it's not going to gain as much. And in 1.0, it's going to lose some weight. If we connect this, or make a line of best fit, where should it cross the x-axis?
0.75.
0.6.
Oh, sorry.
0.6, 0.7, 0.75. If we know what's in the bag is 0.7, what solution should be isotonic to 0.7? 0.7. So this should cross at 0.7. In other words, it's going to cross the x-axis where it's isotonic. So technically, isn't it true that even if I did not know what was in this bag, I could figure it out if I put some beakers with different solutions and graphed my results?
I got you.
And where it crossed the x-axis, that would tell me what was isotonic. So, yes?
Do you know, like, what measurements, like, how big, like...
Well, I didn't put numbers here. The point is, you would actually calculate the percent change in mass and graph those numbers. Which brings us to what I would have to give that to you. Which brings us to what I showed you yesterday. Maybe that clarifies a little more. So here, that means if this is where this one crossed, so it's hard to see, but this was 0. And if it crossed here right around 0.4 or 0.42 or 0.43, that must mean that what was in the bag or the potato or whatever it was 0.43. And that was how we calculated C. Because C represented the molarity of what was in the bag, or the potato, or the grape, or whatever it was we were measuring. Yes?
Just as like a question, T was temperature, C was in the bag, R was the point or something.
0.0821, right?
That you give us.
Yep.
And then what was the lowercase I?
And then I was based on the solute. If it was glucose, I would be 1. If it's ionic,
And that's also given in the...
and that's given. So you're given everything. The only thing you would be left to calculate would be C. And you would calculate it by either looking at a graph that's provided for you, graphing percent changes in mass that are given to you, or in the most difficult kind of problem, you're given the before weight and the after weight, you calculate the percent change in mass, you graph it, and then you get C from there. That would require the most work. However, based on what you did last week, you should know how to do all of those things.
C is where it crosses the x-axis.
So C is where it crosses the x-axis, and the point of C, the whole point, is that represents isotonic. Now that brings us to what we're doing in the lab today. So I'm going to give you potatoes. Okay? You're not eating them. We're not playing Let's Dare who will eat the potatoes. Maybe later.
It's what are the odds?
Oh, what are the odds? I'm sorry.
All
right. Shh, hush, I'm going to run out of time on this recording. All right. So I'm going to give you potatoes. I don't know what the molarity of potato cells is, but I do know that it's somewhere between 0 and 1. So isn't it true that if I put my potatoes in all these different solutions, I would be able to figure out where it crosses the x and therefore the molarity of the potatoes? Okay, but we're going to take it a step further than that. So now it's going to be even harder than that. Oh no, I know, even harder than that. I'm giving you the solutions, but they're all mixed up. You're not told which one is 0.2, 0.4, 0.6, 0.8, or 1.0, or pure water. All I've done is I've color-coded them. So all you're going to know is there's an orange solution, there's a purple solution, but here's the deal. Based on what you know now, in which solution should the potato gain the most weight?
No.
Based on these. Water, right?
Yeah.
So whatever colors water, you'll be able to tell, because that'll be the one that gains the most weight. Which one should the potato lose the most weight?
1.0.
1.0. So whatever color it loses the most weight in, you'll be able to identify that's 1.0. And you should, because you know it's going to do this, you should be able to figure out which is which. That's your first job. And your second job is to figure out the molarity of the potato cells where it ends up crossing the x-axis. Yes. So. All right, so listen, wait. Let me tell you what to do.